Right. So the summary of the last lecture, we have discussed this, we started the basics of this quantum computation and we discussed about the Hilbert space and inner product and outer product. So once again, so let us start from this outer product. Outer product, because today's class this is a very important outer product. So what we have discussed, one more time let me revise. We consider these two state vectors psi1 and psi2 which belongs to the Hilbert space, and the outer product is defined as like this, the product of ket in and bra. So this is the outer product we define, fine. And one more thing what we said, this is nothing but a complex matrix, it's a complex matrix and whose trace, that means the trace of outer product is always equal to the inner product. This is what we discussed, right? Now come to this, it's very crucial. First, projection operator. So today's class is about, I think this is very important, projection operator. What we defined about projection operator, here we have taken outer product two different vectors. If you take a same vector, that is nothing but outer projection operator. That means if you take the same vector, let us say u and u, okay, so this is nothing but the projection operator corresponding to u. And remember, this u must be a unit vector, that means normalized. Unit vector in sense in quantum mechanics it is normalized, that's it, whose magnitude is equal to 1, something like that. Is it clear, sir? Right. Now let us see the properties of this. Yesterday we have explained up to this properties. And what is the projection operator I explained? It will project any vector onto its subspace, that means it is having its own subspace, okay, and if any vector is given, we can project that vector onto its subspace. Is it clear? Right. So properties. Now first one, what is this dagger? Please apply dagger, sir. That means projection operator dagger. U, it's dagger. What dagger will do?
It will do a transpose and then a conjugate transpose actually.
Yes. 1 minute. Okay.
Conjugate transpose.
1 minute. Right. So that means this is the ket vector. Ket will become, bra vector will come to the ket vector and ket vector will go to bra vector. Am I right? So that's why you will be here and again you will be here. That means what? You are getting the same projection operator. Still not understanding? For example, I have taken psi1.
So 1 second. So is there a way we could actually represent what you have written in the transpose thing on a diagram, sir? Is it possible or not possible for this quantum mechanical level?
Diagram means this dagger.
No, sir. This outer product, can we represent it as a diagram? No.
Matrix.
XYZ basis.
Matrix. We will represent as a matrix. That's it, not a diagram.
మనం చేయలేము to understand better అంటారు.
Yemo sir, I didn't think about it. Let me think. I don't know. Let me think about it. Okay. Yesterday we explained about two different things, and today we are asking the same thing. That is, am I right?
Yeah, same thing, but in the sense like outer product ni manu, can we represent it as on a XYZ basis with a vector? That's all. Bomma.
I didn't think so. Let me think. Right. So if you have psi1 and psi2 outer product, if you take the dagger, so what it will do? Ket vector will become bra vector will become ket vector. That's why here it will be psi2, psi1. Is it clear? Right. So that's why What happened here? The Hermitian conjugate of projection operator is again projection operator. Is it okay? So that's why projection operator is a Hermitian. First property. Next, second one.
You get back the same matrix is what you mean.
Yes, yes, yes. If you take the Hermitian conjugate, you will get the same matrix. Next, second property. I would like to square it. Let me check what we will get. Square means again take 2 times pu, of course operator. So that means what is pu? Outer product u into again outer product u. Right? Now see carefully, in the middle what we are having, this is act like a inner product. I think this is nothing but inner product, right? So this inner product is a inner product of same vectors, and that too I told you this must be a unit vector. So that's why this value equal to how much? 1. That's it. Inner product of same vectors is equal to 1 because it is a normalized. So finally if this is 1, what you get? U outer product. Oh, that means if you take a projection operator and square it, you are getting the same thing. So two properties we got, pu dagger equal to pu as well as a pu square equal to pu. Is that clear?
Yes, sir.
Right. So that's it. And the third property is very crucial. For example, I have a system, and let us suppose two basis states are there. Let us say u and v. Two basis states are there. Okay. Now what they are saying is summation over r, summation projection operators. That means sum of all projection operators. Sum of all projection operators is equal to 1. 1 means here I. Okay. That means what? Sir, here how many projection operators? 2. Sorry, how many basis states? 2. Please make a projection operator with respect corresponding to u. Outer product u
Draw
plus
into draw plus outer product of v.
Yes, this should be equal to identity matrix. Always. So this rule is very crucial, called completeness rule. Means if you have a system, you have n basis states. If you take projection operator for corresponding to each basis, let us say psi1 psi1, psi2 psi2, psi3 psi3, and add all those things, definitely you will get identity matrix. Is that clear? I will take an example, then I will explain, then you will understand more properly. Right, sir?
Yes, sir.
Right. So here what we are discussing is very crucial, completeness rule. Completeness rule. Right. So once again what I am saying, for example, you have psi, summation over psi, p psi should be equal to I. Okay. Now I am taking example, let us take Z basis. Z basis are nothing but the computational basis. We will consider as a computational basis. Right. What are Z bases? Ket 0, which is nothing but 1 0, and ket 1, which is nothing but 0 1. Now I request you, please write the outer product for 0 0 and 1 1 and add. That means take outer product here, take outer product here, and add, and tell me what you are getting.
Sure. Two by 1 and 1 by 2. Zero one, 0 1. Sir, first the for the outer product one, neither one is zero, sir. First
Yes,
element one.
yes,
Second the plus one chemo all zeros. The last element is one.
yes, yes, correct.
So finally unit matrix వచ్చింది.
1 0 0 1, so which is nothing but I. Good. And try this diagonal basis also, x basis, and just for practice, diagonal basis. So diagonal basis, how many types are? Two types. One is x basis, another is y basis, but we won't use y basis in our quantum computation. Very rarely we will use. So x basis. Plus 1 by root 2 1 1 minus equal to 1 by root 2 1 minus 1. Please check the completeness rule for this.
Yes, sir.
Take plus plus, take minus minus, outer product, and add.
Into one minus one. Two minus clear. ఇది కూడా clear.
Right, right. 1 minute, sir. Right. You got the identity matrix, right, sir?
Yes, sir.
Right. Fine. So that's it. And here you got some matrix, and again here you got some other matrix, square matrix, and finally we got this 1 0 0 1. So which is nothing but I. So finally we can confirm this completeness rule, that is a summation over psi p psi, which is nothing but summation over psi outer product psi should be equal to 1. I mean I. Right? Okay. Now, so here the next one is very crucial, sir. Listen. Actually, generally if you consider any system, that means Hilbert space we are defining. Yesterday I told you Hilbert space is a I mean it contains only what? State vectors, and the measurements are linear. This is what I said. That means operations are linear and it contains state vectors. That means it's a collection of state vectors. Is it clear? And all measurements are linear. That means measurement is represented by a square matrix, which is a linear operation. Okay, one minute. This is very crucial. Now here we can expand an operator. So here operator is represented by square matrix. Operator is represented by square matrix in outer product form. In outer product form. Okay. Now see, sir, this is very important. Now for example, I am considering a quantum system. First I will take 3 bases or 2 bases. Okay, 2 bases I will take. So that's why I have 2 bases, psi1 and psi2. Okay, so I am considering an operator A equal to a square matrix. Let us say A, B, C, D. It's a square matrix. How can we write this operator in the form of outer product? It's very important for our computation, it's very crucial. So how can we express this operator in terms of outer product of these basis states, right? I will tell you a small technique, sir, please listen. Now take this matrix. Actually this is the matrix representation. Here always we have to write a ket vectors, and here we have to write a bra vectors. What are bases? Ket psi1, ket psi2, bra psi1, bra psi2, and here take the operator whatever you are taking. Clear? Right. Now, so here we are having A, B, C, D, that elements. Now the outer product form of any operator is given by simple, see the board here, very crucial. And what is the first element here? Take that. Now listen, corresponding to A, what is the bra vector? This is what? Bra psi1, bra psi1, right? And corresponding to A, what is the ket vector? Ket psi1. We have to say bra psi1 and ket psi1. Simple, sir. Just make bra as a ket and a ket as a bra. Means corresponding to A, this is the bra vector. Now I am making that as a ket vector. And corresponding to A, this is the ket vector. Make it a bra. Still not understanding. Plus. Next element. B. Please tell me what is the corresponding bra? Make it ket. Ket, that's it. And B, corresponding to B, what is the ket? Yes. Now tell me the third one.
C. So first we have to take the bra vector and convert it to ket. So psi2. And then psi1.
That's it.
B. Psi2 will become ket.
Right? That's it. So any matrix we can write like this. Take an example. Okay, fine. Now I am taking an example. For example, I am taking X gate. So we know X gate is nothing but, X matrix is nothing but 0, 1, 1, 0. Okay, so this X equal to 0, 1, 1, 0, which basis? Z basis, don't forget this. Okay, this is in Z basis. Okay, fine. Now let me write this matrix in the form of this notation. That means like this. Now my matrix is X. My basis states are 0 because the Z basis 0 and 1. Am I right, sir? 1. Now here bra and here ket. Now I request you write the elements and write the corresponding outer product. సార్
పెడుతున్నాను మీకు స్క్రీన్.
ఓకే, ఫైన్. రైట్ ఆ జీరోస్ వదిలేసేసి మిగతా రిమైనింగ్ ప్లీజ్ రైట్ డౌన్ ద రిమైనింగ్ వన్స్. దట్ మీన్స్ స్టార్టింగ్ 0 into that is 0 only, na? Yeah, that's why please take only 1 remaining. That's correct. I think you got the X Pauli X matrix is nothing but this is a 1, okay, into ket 0 bra 1 plus ket 1 bra 0 finally.
1 bra 0, okay, plus ket 0 bra 1.
Same. Maybe into 1 is there, I need not to consider, na? So this is the outer product form of this matrix. Now please write the head mod. No problem. It is easy, very easy. Same head mod is also we have written in the Z basis. 0, 1. Please write. You will get confidence. 1 by root 2 outside. Yes. అన్ని 4 టర్మ్స్ ఉంటాయి. 4 టర్మ్స్ విల్ ఎగ్జిస్ట్. సార్ మీరు ఫస్ట్ కెట్ రాస్తున్నారా? ఫస్ట్ బ్రా కన్వర్ట్ చేయండి. ఫస్ట్ బ్రాని కెట్ కన్వర్ట్ చేయండి. ఎందుకంటే ఆర్డర్ ఈజ్ ఆల్సో వెరీ ఇంపార్టెంట్. అంటే ఇప్పుడు మీరు ఫర్ ఎగ్జాంపుల్ ఇది ఉందండి, ఓకే, దిస్ ఎలిమెంట్ ఈజ్ దేర్, ఓకే, మీరు బై మిస్టేక్ ఈ కెట్ని బ్రా చేశారనుకోండి, ఈ కెట్ని బ్రా చేస్తే పోతుంది, ఐ మీన్ మీరు ఓకే ఫస్ట్ బ్రాని కెట్ చేయండి, అది నేను అంటుంది. ఓకే ఫైన్, అదే నెక్స్ట్ నో ప్రాబ్లం. ఓకే ఫైన్, ప్రొసీడ్. Yes. రైట్, ఓకే కనపడుతుంది. రైట్, కరెక్ట్, రైట్ సార్, పర్ఫెక్ట్. ఇక నెక్స్ట్ టైం నుంచి ఈ 1 ఉన్న చోట 1 ఇంటూ రాయకండి, డైరెక్ట్గా రాసేసేయండి. ట్రై చేయండి నెక్స్ట్ టైం నుంచి, లైక్ దిస్. సో ప్లస్ హియర్ ఈజ్ అ 1, దిస్ ఈజ్ ket 0 bra 1 and this is a 1 ket 1 bra 0 and here is a minus, that's why minus, this is a ket 1 bra 1. Right sir? Right. Now the next one, it's very important. Now here let me take a diagonal matrix. Actually this is also very important sir, outer product form only. That means what we are discussing is a matrix in the form of outer product. Right. Okay. Now I am taking a diagonal matrix. Now see. So could you please tell me one example? Diagonal matrix means I am taking like this: A11 0 0 0 0, sorry, A22 0 0 0 A33. Is it okay? Right. And now, so please tell me what are these diagonal elements? Eigenvalues. For every diagonal matrix, eigenvalues are simply diagonal elements. Okay? Is it okay? Right. Now see, okay. So whenever you have a diagonal matrix, eigenvalues are simply diagonal elements. Diagonal elements. Now, what are these diagonal elements here? A11, A22, A33. I don't know whether you remember this A11, A22, A33. If you find the corresponding eigenvector of A11, you will get this. Am I right? A22 eigenvector 0, 1, 0. A33 0, 0, 1. This is what I told you in my another lectures. That means if you make all these bases together as a columns, then you will get identity matrix. Okay, fine. So now please write this in the outer product form. Let me write. This is my operator. So I have, sir, please take it as 0, 1, 2. 0, ket 1, ket 2. No, no need to consider 0, leave it. Only consider non-zero elements. Right, 0, 0, right, 2, 2, correct, that's it. That means A11 outer product corresponding to its basis, I mean its eigenstate. A22, this is the eigenvalue, its corresponding eigenvector is this one, outer product, plus A33, and this is 2, 2. Am I right? This one you got. Okay. Now, if you observe carefully, shall I split this matrix like this? Okay. Now tell me, what is this?
Not a unitary matrix, but somehow close to it.
No. Please observe this and this expression.
Oh, so this is an outer product.
Yes, outer product of 0, 0. So this is the outer product of 1, 1. This is the outer product of 2, 2. And what are A11, A22, A33 eigenvalues, right? Eigenvalues. And this is the eigenvalue of this, lambda of this, lambda of this, and this is the lambda of this. So finally, what is my conclusion? If you observe carefully, any matrix, sir, this is valid for any matrix, any operator, any matrix, I mean square matrix, I'm sorry, any square matrix. Any square matrix can be written as just like this: A, B, C, D, E, F, G, H, I. Let us suppose some arbitrary matrix. Anything can be written as like this. eigenvalue corresponding outer product, eigenvalue corresponding outer product of its eigenvector plus eigenvalue into corresponding outer product of its eigenvector. That means lambda 1 outer product psi 1 psi 1. I hope you got this. Next lambda 2, what is its corresponding eigenvector outer product? Psi 2 psi 2 plus lambda 3 psi 3 psi 3. Okay, but we should check always whether it is normalized or not. That's why we have to divide with its inner product. If it is normalized, mean it should be normalized. If it, in case it is not normalized, the denominator is not equal to 1. Okay, so by inner product psi 2 psi 2. Sir, why we are writing that a denominator? Mean just to confirm it is normalized. If it is normalized, the denominator won't be there. See, here there is no denominator, here there is no denominator, here there is no denominator. Yeah, 1 divided by, yes. Or simply yesterday I told you one technique. Numerator we are finding already, it's a matrix. Denominator is nothing but its inner product. Inner product is nothing but the trace of this outer product, right? That's why no need to write this. Simply we can say this is the trace of numerator. Because already we are writing numerator. So this is nothing but, you understand this point, sir? Trace of numerator. This is nothing but trace of numerator. That's it.
Sir, ఇప్పుడు I don't know if it is related to this or not.
Which one?
You've been mentioning eigenvalues and eigenvectors. So, what is an eigenstate and what is an eigenvector? What is the difference?
What is the difference? Okay. Now for example,
ఎందుకంటే వాడు కంప్యూటేషనల్ బేసిస్ స్టేట్ లో ఇట్ విల్ కొలాప్స్ టు ఐగెన్ స్టేట్ అని చెప్తుంటే రాస్తుంటాడు, మనకేం అర్థం కాదు. అంటే తర్వాత వస్తుంది అంటే అప్పుడు తర్వాత డీల్ చేద్దాం.
and I think you said already you know about eigenvectors. That's why I didn't I'm not discussing that. Eigenstate అంటే ఏంటి అంటారా? That's what you are asking.
So why it collapses?
Why collapses, next one we will discuss. That is the postulates. Why collapses I will explain, and what is the reason behind that. Okay.
నా మనసులో ఒక అనుమానం చెప్పేసాను సార్. It collapses only into an eigenstate అని రాస్తాడు ప్రతి పుస్తకంలో.
అవును, that's I told you yesterday, every quantum system can be written as a superposition state of its basis states, right? Basis states are nothing but eigenstates. Just now I said I consider one system, okay, so which is having psi 1 psi 2 psi 3, something like that. Somewhere I have written here. See this, what I have taken basis.
Psi 1, psi 2.
These basis states are nothing but eigenstates, sir.
It's only a jargon ante.
Its basis states are nothing but eigenstate. Every quantum mechanical system can be written as a linear combination of basis states or a linear combination of eigenstates. Once you make a measurement, definitely it should be in one of that. For example, you have 3 chairs and I am outside the room, okay, so if I make a measurement on your position, definitely will be in one of the chair. As long as I am not measuring, you will occupy 3 chairs. I hope you understand. Okay, so once I measure, so that superposition collapse and you will be in one of the state. Just like a teacher is not watching the classroom, students will go everywhere. Once teacher is watching, they will stay in their position, something like that. Right, okay. Now that's it, and yeah, fine. Now let us move this to 1 minute, sir. Yeah, Outer product sigma x, sigma y, everything is completed, and this is also completed. Cool. Right. Now, so please take a fresh page and put the headings are postulates. Postulates of quantum computation. Right. Ready, sir? Right. Okay. So what is meant by postulate? Quantum mechanics, classical mechanics, quantum computation, it's a different. What is meant by postulate? A set of assumptions. That's it. Set of assumptions. Set of assumptions to describe a system. Here it is our quantum system. Fine. Sir, for example, I have given a quantum system to you, just like this. Some quantum system given to you. First, what you will do? What is the process? How you will study? How to study? So, for example, I have given this. Let us say this is a quantum system. I have given to you. I ask you what are the properties of this quantum system. First, what you will do? How to represent this quantum system in Hilbert space, right? Because every operation is coming from there only. Because we have to represent our quantum system as a superposition or a linear combination of its basis states. Where these basis states exist? Hilbert space. So that's why first any quantum system must be represented in the linear combination of basis states. Is it clear? That's why our first step is a representation of quantum system. This is our first postulate, sir. I hope you understand the order. After representing a system, what you will think? Okay, I know the system at morning 5 o'clock. What could be the system at evening 5 o'clock? That means how it is changing with respect to time, right? That is your next step. That means I prepared a system, but how it is varying with respect to time, whether it is changing or not. It will be like this as it is, or whether it is changing or not. That means we will study how the system changes with respect to time. Is it okay, sir? Next step. What could be the next step? Okay, now you understand whether it is changing with respect to time or not, you understand. After that, what you will do? Okay, let us make a measurement. Let us find its energy. Let us find its position. Let us find its momentum. Because, for example, in classical mechanics, generally, whenever you are going by on a bike, okay, you want to measure the speed. What we will do? There is a speedometer. If we want to measure our weight, what we will do? A weighing machine is there. In classical mechanics, there are ready-made devices. That means if you want to measure the length, there is a tape, scale, something like that. So all classical measurements are having some devices, ready-made devices. But how we will measure in the quantum mechanics? We don't have any devices. If a position is measured perfectly, momentum is going. If momentum is perfectly measured, then position is not uncertain. Position is not certain. Then how to do this? So the next postulate is about measurement. Measurement on quantum system. Okay. And the last and final. So once you have done the measurement, That means you are finding some physical properties, physical quantities, whatever it is. If I want to find energy, I will operate energy operator. If I want to find momentum, I will operate the momentum operator, something like that. Measurement. Once you have done the measurement, what you will think? Okay, I have studied only single system. If I have 100 systems, what to do? That is composite system. How to get a composite system? That is about the next one. I hope you understand. First we are taking a one system and we are representing it, and we are checking whether it is how it is changing with respect to time, and after that we are going for the measurement, because here also we will measure how it changes with respect to time. After that, okay, I don't have this one single system, I have many systems because n electrons are there. I won't write at a time for n electrons. First I have to know for one electron, then I will go for how it will be for n electrons. Because for 1 qubit you will write the states are. For 2 qubits, by using that only you are writing? Say yes or no? So because at a time we are not writing for this. First what you are doing, you are taking a single and you are making a composite system. Like that. That is about the next postulate. So these are the quantum computation postulates. Number 1, number 2, number 3 and 4. So whatever your doubts, everything is with this. Okay, if you understand this, then only you will understand density matrix and all those things. Whatever the problems he has given in that book, we can do all those things. No need to worry. Right? Okay, let us start one by one, because we will come in the order. First postulate. So this is clear?
Yes, sir.
Right. Now first postulate. First postulate is simply a representation. Okay. Representation. Now whenever we have a quantum system, so what we have to do for that quantum system, we need to construct a Hilbert space. This is my Hilbert space. Now let us suppose this Hilbert space is spanned by basis vectors. Basis vectors of the system. Am I right? Sir, how do you know basis vectors? That's the problem. We have to first assume in which basis you are going to construct the system. Sir, Z basis, okay, proceed. Or X basis, okay, proceed. First we have to set that in which basis states we are going to express the system. Is that clear?
Yes, sir.
Right. So once you decided the basis states, now this Hilbert space is completely spanned by these basis states only. Okay. Now what you are doing is, I have a quantum system. Okay. So now how to write this?
Sir, one quick question. Psi 1, psi 2, psi 3 are they Z basis, sir?
Whatever you please assume first. In which basis you want to express, that is up to you. That means if you want to take Z basis, that is 0 and 1. If it is X basis, plus minus. We can express the system in any basis, sir. We can transform one basis to another basis. Alright. I am taking more generally because Z basis contains only 2. I have taken 3, that's it. Okay?
Sir, that's the question that I had. Yeah.
Oh, this is not a Z basis actually. I will explain in the example. This is more generally I am taking. My system is having these 3 bases. Right. Now, this is my quantum system that is represented by wave function. Okay. So how to write this wave function? This is what I am saying is, if you measure a quantum system, definitely it will be in any one of the bases, right?
Correct.
That's why always the quantum system is a linear combination of bases. That's why I can take A1 psi 1 plus A2 psi 2 plus A3 psi 3. I can write this as summation over I AI psi I. Okay, sir? Right. Now, okay. So, come to this basis states. In our quantum computation, we have some basis states. Let me explain this. So generally there are three basis states, sir. One is Z basis, another is X basis, another is Y basis. We can represent our quantum system by using any of these bases, but people are generally considering this one, computational basis, general basis, general, and these two are called diagonal basis. Okay, sir? Right. Now, so what are Z bases? I hope you know. This is 0. Yes, 0 and 1. So I think this is a 1 0 and this is a 0 1. Good. Now what are X bases? X bases are nothing but one is a plus, minus. Yeah, 1 by root 2, 1 1, 1 by root 2, 1 minus 1. Next one, this Y bases. Y bases are represented by rotation, sir. Clock, anti-clock. So this is a 1 by root 2, 1 iota, 1 iota, 1 by root 2, 1 minus iota. So these are the three basis states possible for our quantum computation to express any system. But we are choosing only this one. That's it. Okay? Right. Now,
theoretically speaking, ఇవి మూడు మనం ఫర్ ద హ్యూమన్ మైండ్ చేస్తున్నాం కానీ ఇట్ ఇస్ ఇన్ఫైనైట్ సార్ యాక్చువల్గా అయితే మనం ఏదైనా తీసుకొచ్చాం మనకి అంత
ఏదైనా తీసుకోవచ్చు because one thing can be converted into other.
కాదు ఈ మూడు కాదు బికాస్ ఇట్స్ హిల్బర్ట్ స్పేస్ యాక్చువల్గా నా క్వశ్చన్ ఏంటంటే బికాస్ ఫర్ హ్యూమన్ మైండ్ అండ్ క్యాలిక్యులేషన్ ఈజ్ మనం ఈ మూడే తీసుకుంటున్నాం బట్ జనరల్గా మన ఇష్టం వచ్చిన ఇంకొక కాంపిటేషనల్ బేసిస్ కూడా తయారు చేసుకోవచ్చు.
You can create, yes. But the thing is, we can create a basis, no problem. That is the orthogonalization process will be there and we can create, no issue. Actually generally any subjects are first they want to make it easy. Okay, that's why they are going for this. Why they are not going for this means little bit calculations will come, more calculations will come. That's why they are going for this. Right. That's it. This is about first postulate. So first postulate, this is a representation of a quantum system which is a linear combination or superposition of all basis states. That's it. Clear. And we can consider any Z basis or X basis or Y basis. Fine. Next one, postulate 2. Right. So what is this? Yes. Yeah, please. Sir.
But if you pull that into the Z basis, there are only two states, so I will have only A1 psi 1 plus A2 psi 2.
Exactly. Let us write one example if you want. So in our qubit state example, our qubit state alpha, shall we I think it's better to discuss, sir. Wait, it's better, it's nice, good question. Right. So what we understand is psi is a linear combination of basis states. Okay, fine. Now let us take an example. Now I am taking Z basis, so that is ket 0 and ket 1. Now how we will write our qubit state? Our qubit state in Z basis, how we will write? I hope you remember, that is alpha 0 plus beta 1, where alpha and beta belongs to the complex numbers. That is a1 psi 1 plus a2 psi 2. Is it clear, sir? Wait. Now in x basis, so could you please tell me how to write this in x basis? My qubit in x basis.
Okay, so it will be whatever alpha.
Yes, you can take alpha, no issue.
Alpha of plus.
Yes,
Beta of minus.
beta ket minus. Right? That's it. So this and this both represent same, sir. Only the thing is, what we are doing is we have converted the basis. I mean, we have chosen the different basis. This is the qubit in the Z basis. This is the qubit in the X basis. Earlier I told you, sir, we can convert from one basis to another basis. So let us try this also. Why don't we try? Okay, sir. Now.
And then I was just trying to connect to that yellow thing. Psi is equal to sigma I a I psi I. That's all.
Yeah, this also will do, because it is very useful for the next one.
Okay.
Now earlier I said, what is a plus? 1 by root 2 1 1. Now I think I can write this as 1 by root 2 1 0
Plus
0 1. That means ket 0 plus ket 1. That's good. Now minus can be written as 1 by root 2 ket 0. That's it. Now if I add this, what I will get? If I add this, ket 1 gets cancelled. Here I will get 2 by root 2 ket 0. That is nothing but root 2 ket 0. Then ket 0 is nothing but, ket 0 is nothing but 1 by root 2 ket plus ket minus, check. Otherwise I will write one more step.
No. This is clear, sir. This 0 0 cancel అయిపోయి.
ఈ 1 1 cancel అయినాయి. 1 1 cancel అయినాయి.
అదే 1 1 cancel అయిపోయినాయి. So 2 మీకు 2 get 0 వచ్చింది. 2 by root 2. So root 2 of ఇలా అయిపోయింది.
Yes. So finally ket 0 equal to 1 by root 2 ket plus ket minus. Am I right? Yeah, similarly please tell me ket 1.
1 by root 2 get plus minus of minus.
Right. Now please see. Come back to this. Now you are in which basis? Z basis. Now I would like to, now I am in the Z basis. Now I would like to represent the system in the X basis. That's why alpha ket 0 is nothing but 1 by root 2 ket plus ket minus. Is it okay? Plus beta 1 by root 2 ket 0 minus ket 1. Now please take the common, sir. This is alpha plus beta. I'm sorry, something. No, here plus minus. Yeah. So please take a common plus, sir. Is it okay? Next, take common minus. That means minus state common. Then it is alpha minus beta by root 2. So see, this is our qubit in Z basis. Earlier we have written, so you should not take alpha as it is. It is alpha prime and beta prime. This alpha prime is nothing but this. This beta prime is nothing but this. So we can rewrite in any basis. It's not an issue. Fine? Any doubts, sir?
No.
Right. Next, postulate 2. Right. So what is this postulate 2? Okay. Now postulate 2 is about what? What I explained. Now we already represent the quantum system. How the system is changing with respect to time. That means how dynamically varying. How the system varying dynamically something or varying with respect to time. Fine. So this is from Schrodinger's equation. So what is the Schrodinger's equation? IH cross dou psi by dou t equal to H cap psi. What is H? No, H cap. Hamiltonian of closed system. Sir, important. Hamiltonian of closed system. What is meant by closed system? No. Energy. Only energy is exchanging between the particles like that. Actually, isolated, closed and open. Open system means particles will exchange. Closed system means only energy will exchange. That's it. Right. Okay. That means only energy changing. No number of particles. For example, if I have a system of 100 electrons, after some time also 100 electrons only. After some time it become 80 electrons means what? The number of electrons are exchanging. That is called open system. So closest means only energy, right? That's it. And here we need to, sir, this is important. IH cross dou psi by dou t equal to H psi. What is the issue with the Schrodinger's equation? We won't use this Schrodinger's equation form in quantum computation. The reason is this Schrodinger's equation is having continuous in time. Continuous in time. That means it takes all values from 0 to infinite, all some continuous in time. But our quantum computation is based on a discrete system, discrete states. That's why we have to rewrite this. Now wait. So this is the first order differential equation. I hope you have an idea. This is the first order differential equation. So what I am taking is IH cross dou psi by dou t equal to H psi. Sir, the process is variable separable. That means bring psi one side and other things other side. Dou psi by psi, I am bringing this side. Then H as it is, I am bringing the constant this side and time this side. Is it okay? Now integrate. Now I am assuming at a time t equal to 0, psi naught. At a time t, it is psi of t. Initial 0 and final time is t. Dou psi by psi is nothing but log psi. Because integral of 1 by x, log x. This is a psi of 0 and this is a psi of t equal to h cap will be as it is. I think I can write it as a minus iota because I can bring this iota here by h cross. Integral dt is nothing but a t. Am I right? Now, please substitute the upper limit and lower limit. Log. Which one, sir? 1 by iota. 1 by iota is nothing but minus iota. ఒక్క నిమిషం చెప్తాను. Iota, okay? Just multiply with iota on numerator and denominator. Right. So, okay. Right. So, now upper limit log of psi of t minus lower limit log of psi of 0. Is it okay? Equal minus I h cap t by h cross. Now this is nothing but log psi of t by log psi of 0, log a by b. equal to minus iota h cap t by h cross. Finally, psi of t can be written as, because this is equal to exponential, I hope you know this, log of x equal to y, then x equal to e raised to y, then psi of t equal to e raised to minus iota h cap t by h cross, and here we are having psi of 0. Is it clear, sir? Now I would like to write in the Dirac notation psi of t equal to, this is my operator, e raised to minus iota h t by h cross into ket psi of 0. Okay. If I know the wave function at a time t equal to 0, if I want to get the system state after some time t, I have to multiply with an operator. This operator is unitary operator. How do you know, sir, it is a unitary operator? Take it and apply dagger and multiply, you will get 1. That means a unitary operator dagger, sorry, identity అనకూడదు, u dagger into u equal to I is called unitary operator. ఏది I అంటే ఐడెంటిటీ మ్యాట్రిక్సే. I means nothing but identity matrix. So finally what they are saying is psi of t equal to, this is a u of t, or simply u operates on psi 0. This is the reason why we are using this Schrodinger equation in this form, because the Schrodinger equation is having continuous in time, and now it become a discrete. Means discrete means I have a linear combination, I want to find its time dependence, I will operate u on that only, I will operate u on another one, I will operate u on another one, then I will get the final state. So that is easy, I mean discrete, that is in the form of a discrete nature, something like this. Got it, sir? మీ ఇష్టం, అంటే after what time, whatever time you want.
So I'm not forced, if it was integration, I'm forced to go through continuous values.
Yes. Yes, for example, I want to study how the system is changing from t naught to t only. This is the advantage, t naught to t only. Then what I will get? Psi of t equal to some operator into psi of t naught. Now this operator contains both t naught comma t, right, which is nothing but e raised to minus iota, sir, h t by h cross. So Hamiltonian, this is a t minus t naught by h cross. That's it. So this is about postulate 2. Shall we start, or is it okay? You want any break? Okay. నాకు అంటే 8:45 ఒకసారి క్లాస్కి వెళ్ళి జస్ట్ క్లాస్ ఆన్ చేసి వస్తాను. నేను అట్లాగా ఒక 10 minutes బ్రేక్ అవుతుంది. Right. Now this is the postulate 3. I will explain little bit slow, sir, because this is crucial. Measurement. That's what I am asking. You want any break, or can you continue like that? That's what I am. 8:45 రైట్ 8:40 ఆల్రెడీ 8:40 అయింది అందుకు. ఓకే, ఒక 10-15 minutes, I mean 15 minutes బ్రేక్ తీసుకొని మళ్ళీ కంటిన్యూ. మీకు పర్లేదా? టైం ఎంత అయింది మీది మరి?